Okay, we're going through the Spec Maths practice exam for semester 1. Make sure you've got your formula sheet on you and your calculator. So let's make a start. We got this one here. What we need to use is one of our circle theorems. So it's this very first one here, angle in a semicircle. So you can start by saying angle CDB is 90 degrees, and you can say angle in a semicircle theorem. So we can go and label that as 90 degrees. Therefore, x plus 90 plus 64 is 180. And this is sum of angles in triangle BCD. Therefore, x would be 180, take away all those. So 180 take 90, take 64, which equals, and we can work that out. So best to just chuck it in your calculator just in case. 180 take 90 take 64, 26. Okay, next one we got here. So we're going to need another theorem. So this one here, well, we've got a couple theorems we can look at. So CFE is 66 degrees. Now these are vertically opposite angles. So that should be 66 degrees just in there. Another angle we can work out is the one across here. So there we go. 56 is across there. Angle FEC. That's 56 degrees. And this is, let's see what that theorem was called, angles subtended by the same arc. That's 56 degrees. And then x plus 56 plus 66 equals 180. And this is sum of angles in triangle FEC. Therefore, x would be 180, take 66, take 56, and we can work that out. 58. Now, there is actually a slightly faster way you can do this. One less step than what I did, so I'll be curious to see if you can spot it. Have a think about that one. Okay, O is the center of the circle there. So we have to find the angle ACB. So a couple of things we can do. So, well, we can look at this angle in here and this angle in here. So angle OBA equals angle OAB as triangle OAB is isosceles. So OB and OA are both the radius. Okay, so that's good. Therefore, angle OBA times 2 is plus 72 is 180. Therefore, and we can rearrange this, angle OBA is 180, take 72 all over 2. And we can work out what that is. 54. So what we've learned here is that because these are both a radius or isosceles, this is 54 degrees and 54 degrees in there and there. A couple more angles we can work out. So angle CBO is 90 degrees. Now this is the radius tangent theorem. Therefore, angle CBA is 90 take 54, which is something we can work out. 90 take 54, 36 degrees. So what we're saying here is this whole thing was a right angle, so that should be 36 degrees in here. 36 degrees there. All right, and then we can find this angle in here, 54. So that's going to add up to 180 because it's a straight line. Okay, so 54 plus angle BAC, 180. And this is supplementary angles, so angles on a line. Therefore, angle BAC would equal 180 take 54, 126. So we can plot that in there, 126 degrees. And then one more step, 36 plus 126 plus x is 180. And this is a sum of angles in triangle BAC. Therefore, x is 180 take 36 take 126, which is whatever that is, 180. 18. Cool. So that's how I do that one. Next, we got this lovely question here. There's actually a couple of different ways we can approach this. Best way to deal with this is to use the angle at the center theorem. Tells you that's 40 degrees there. 40 degrees in there. So angle ACD equals half of angle AOD. And this is angle at the center. So if we have a look at what that theorem says, where is it? Angle at center. We've essentially got that very first little subcase of angle at the center. Okay. ABDC is a cyclic quadrilateral. Therefore, 40 plus x is 180. Therefore, x is 120. All right, so that's one way you could do it. The other way that you could do it is you could look at the other side of the angle there. That's 240 because they have to add up to 360. And then that one is half by angle at the center theorem. So there's a few different ways you can approach that problem there. Okay, but it's 120 regardless. Consider this circle with a radius of 5 and a center O. So the length of ED is 8. There we go. So EC equals CD, which equals half of ED. Now this is one of the early theorems, quarter of a circle theorem. Because that's 90 degrees in there. Okay. Therefore, EC is 4 centimeters. So we'll label that as 4 centimeters there. This one is 5 centimeters. So OE is 5 centimeters, and that's the radius. That was given in the question. Therefore, the length OC squared plus CE squared is OE squared. This is Pythagoras on the triangle OCE. And we can just fill in what all those bits are. So OC squared we don't know, but I do know what the other ones are. So that's 4 squared equals 5 squared. So OC squared is 5 squared take 4 squared, which is 25 take 16, so it's 9. So OC is 3 centimeters. Well, it's plus or minus 3 centimeters, but it's got to be positive. So yeah, positive 3. So that's that length in there. Therefore, BC is 2 centimeters. As BC plus CO is 5, which is the radius. Cool. So yeah, that missing link there is 2. All right. Find the angle PQS. 56 plus 90 plus the angle PQS should all equal 180 degrees. Now this is sum of angles in the triangle PQS. Therefore, angle PQS would be 180 take 56 take 90. We can work out what that is. 34. Okay, so I might mark this on the diagram there. That is 34 degrees. Now, next is to show that QRP equals 34. Angle QRP equals angle PQS. Now this is, I think it's the tangent chord one. Yeah, this one. Angle between tangent and a chord. So angle between tangent and chord theorem, which equals 34 degrees. That's what you wanted. So that's 34 down there. Hence show that QPR. This is very similar to the first question, 56 degrees. So angle PQR is 90 degrees. So this is angle in a semicircle theorem. So that's 90 degrees there. Therefore, 90 plus 34 plus angle QPR would have to equal 180. So this is sum of angles in triangle QPR. Therefore, the angle QPR would be 180 take 90 take 34, which is, all right, 180, 56. All right, beautiful. So I'll just label that on there. Really importantly, 56. Now it's actually true that these two angles here, the 56 up the top there and the 56 we just found, they always match. And that's something you can try and prove in general for this question. All right, SP is 2, QP is 4, find PR. Now this is a really, I would say it's one of the harder questions on the exam. But once you see how to do it, it's not too bad at all. I'm going to draw these two triangles, PSQ. PSQ. And really importantly, 56, 34, 90. I'm going to draw this other triangle, PRQ. Guess what? Exactly the same angles. 90, 56, and 34. Therefore, they are similar triangles. So you could say like triangle PQS is similar to triangle PQR. All right, now let's just make sure we've got, I think we've got all those in the right spot. So basically we've got some links here. So SP was supposed to be 2 centimeters. Yes, I've got those the wrong way around in the first one. Q should be up there. I was second guessing myself there. All right, SP should be 2. So we've got this length here is 2 centimeters, and it said that QP is 4. So this length here is 4 centimeters, and also this length here is 4 centimeters. Now, how much bigger is the second triangle than the first? Well, what you do is you line up a common side. So this is 90 and 56. This is also 90 and 56, there and there. So that means that this was 2 and this was 4. So we've actually doubled the triangle there. So they're twice as big. So that's how similar triangles work. One of them is a scale multiple up of the other one. So what we'd need to do is we'd need to, well, we know that to get from 2 up to 4, that is times by 2. So that means to get from 4 up to the side we want, I need to times by 2. So that would be 8 centimeters. So therefore, PR is 8 centimeters, as they're similar. So yeah, that bottom triangle is just twice as big as the top triangle. Okay. Vectors, V plus W. So that's 7 plus 4 and minus 2 plus 5. V take W. Make sure you underline these as well. So that's 7 take 4 and minus 2 take 5. So minus 7. For V take W. So 4V take W would be, let's write out 4V first. That's 28 minus 8. And W, so take 4, 5, which equals 24 and minus 13. Find mod W. Mod W is mod of, well, it's root 4 squared plus 5 squared, which is root of 16 plus 25. And let's work that out. Root 41. We'd like to find a vector parallel to W but with a length of 3. So W hat is 1 over root 41. Well, I'll put out the formula first. 1 over mod W, which is 1 over root 41 times the original vector. I think it was 4, 5 for W. This is 4 over root 41 and 5 over root 41. So this one here has a length equals 1. So therefore 3W hat, which is 12 over root 41, and 15 over root 41. This should have a length of 3. So what you do is you scale it down to the unit vector that's got a length of 1, and then you scale it back up to have a length of 3. Alrighty, sketch these 3 points on a Cartesian plane. So there's 5 there and there's 5 there. So A is 2, 5. B is 4, 8. And C is 5, 3. And D is 7, 6. All right, beautiful stuff. Note that AB is 2, 3. So how we got that is 2 up to 4 is 2 and 5 up to 8 is 3. So we need to find AC and AD. AC is, how do I get from 2 up to 5? So that's 3 and 5 to 3. So minus 2, just like that. Okay, and we want to find AD as well. AD is, let's see, 2 up to 7, so that's 5. And 5 up to 6, that's 1. Okay. Show the ABDC as a rhombus. So, I mean, it certainly looks like a rhombus, because if we join these up, it definitely looks like those are all the same length. And I've given you a little hint here. All you need to do is show that one pair of opposite sides. So maybe let's go, we want to show AB is parallel to CD and mod AB equals mod CD. So let's see if we can do this. So AB we already have. So that is 3 minus 2. And CD we can get, so it's 5 up to 7. Let's see. AB. Ah, sorry, my bad. I read off AC. AB is 2, 3. That was that vector up there. And CD, 5 up to 7. So that's 2. And then 3 up to 6. So that's also 3. So actually, AB equals CD. Therefore, these two are satisfied. So those two conditions are satisfied. Therefore, ABDC is a rhombus. Now, if you're wondering why I'm putting the letters in a weird order, when we talk about a rhombus, ABDC, you sort of go around the points. So ABDC. If I wanted the rhombus ABCD, I would have to swap where C and D are in that diagram. So just be really careful. Show that AD dot BC equals 0. So AD we worked out before. AD is 5, 1, and BC we can also get. So 4 up to 5 is 1, and 8 down to 3 is -5. AD dotted with BC, it's 5 times 1 plus 1 times -5, which is 5 take 5, which is 0. Therefore, AD is perpendicular to BC. That's what it means when the dot product is 0. Therefore, the diagonals are perpendicular. They're at right angles. So basically, if I draw in the diagonal lines, and there's a right angle there. Good. Next question. Well, next part of the question. Calculate these two angles. So we can go BAD as the angle is inverse cos of AB dotted with AD over mod AB mod AD. And we actually worked out what all these vectors were before. So AB and AD, I might just note them again. AB was 2, 3. AD was 5, 1. All right, groovy. So that is cos inverse of 2 times 5 is 10, and 3 times 1 is 3. Mod of AB is root of 2 squared plus 3 squared. So that is 4 plus 9. And mod of AD is 25 plus 1 under the square root. You can do that in your head in one step if you want, but I'm just stepping it out here. So that's cos inverse of 13 over root 13 and root 26. Okay, we can work this out. So if we go into degrees and go into our matrix, inverse cos 13 on the top, root 13 on the bottom times, and then root 26 on the bottom. Groovy. All right, 45. Oh, that's pretty cool. 45 degrees. Wonderful. And what that means is that basically that angle that we just calculated in there is 45, and we're about to find that other one. And spoilers, it's going to be 45. Okay, so now we want to calculate CAD, angle CAD. So that's AC dot AD. You've got to point the vectors out from the angle you want, and then mod AC, mod AD. Okay, so AD is there, AC. I think we had it before. Where was it? 3 minus 2. All right, 3 minus 2. So that's the dot product there. Oh, this also needs a cos inverse around it. The dot product there is going to be 5 times 3, so that's 15. Take 2, that's 13 on the top. And that's root 26, root 13. Interesting. That's going to give us exactly the same. I don't even need to put it in the calculator as 45, because we just literally did it back there. The only thing is the bottom swaps, but if you're timesing two numbers, it doesn't matter if you swap the order. Hopefully your two angles from part E were the same, and yes, they were. Now, we've basically shown two properties of the rhombus. So I'll draw it on this diagram here. One property that we've shown just in that very last bit there is that if you take a diagonal, these two angles are the same. So that's this one here, the diagonal bisects the angle. And then the other one we've shown is that if you take your two diagonals, then they're at right angles to each other. So that was that first one that we showed. I want you to do just one of the two properties. I don't expect you to prove both. I'm going to prove both in the solutions just in case. So option 1 is just so that if you did do both, or if you did one or the other, you don't miss out on the answer. We want to show that BC is perpendicular to AD. So those are the diagonals. So BC dot AD equals 0. That's our want to show. I might actually put that in red. That's what we'd like. So let's see. BC as a vector is BA plus AC, which is minus P plus Q. And then AD as a vector is AB plus BD, which is P plus Q. And if we look at BC dotted with AD, these all need lines above them, BC and AD. That is, I'm going to write that as Q take P. Q take P. And I'm going to write the other one as Q plus P. Q plus P. All right, so we're going to get Q dotted with Q plus Q dotted with P, take P dotted with Q, plus P dotted with P. And I think the last term is negative because you got minus P. Cool. The middle two terms will cancel off. So that is Q dotted with Q, take P dotted with P. There's a dot product identity, mod Q squared take mod P squared, which is 0 as mod Q equals mod P. Those distances are the same because it's a rhombus. Therefore, we did what we want, BC AD. So that's option 1 if you want to prove that. And that's actually the easier option. Option 2. Okay, we want to show that the angle BAD equals the angle CAD. That's what we'd like to show in this option. Okay, so we can work out each bit. So cos of angle BAD is AB and AD over mod AB mod AD. So that's, we actually worked out what these were before, I think. Well, AB is P anyway, dotted with, and AD is P plus Q. Over, mod AB is mod P, and that's mod P plus Q. We can FOIL out the top, so that's P dot P plus P dot Q. And then that's mod P plus Q on the bottom. And then the top, P dot P just becomes mod P squared. That's a property of dot products. Mod P plus Q. All right. And then if we look at cos of angle CAD, it works out to be very similar. So it's AC dotted with AD over mod AC mod AD. So AC is Q, and then AD is P plus Q, omega Q plus P, and then that's mod Q mod Q plus P. Okay, if we FOIL out the top, you get Q dot Q plus Q dot P over mod Q plus P. So that's mod q squared plus p dot q on the top. I'm just going to swap the order. And then that's mod q mod p plus q on the bottom. Okay, these are both equal as mod p equals mod q. So the only difference in the formula is that top left bit, p squared and q squared, but they're the same if mod p equals mod q. And then the only other thing that's different is on the bottom you've got mod p and mod q. So yes, angle bad equals angle CAD. Cool. So just one of those two, please don't do both. Prove that A, B, and C are collinear. So this one here, we need to look at the vectors A, B. So that vector is 4, 2. And we need to look at the vector AC, and that vector seems to be 6, 3. And therefore AC is 1.5 lots of AB. So therefore AC is parallel to AB. Also, they have shared point of A. So if you've got these two lines, AC and AB, and they're parallel, but they happen to both share this point A, which is on both those lines, then they're not two separate lines. They're actually the same line. They're actually just sitting straight there on top of each other. So the point is they're collinear. Therefore, A, B, C are collinear. Wonderful. Find a point X which divides AB in the ratio. I might get rid of that diagram. That'll just be confusing if you read the solutions. Anyway, find X which divides AB in that ratio. So essentially what we're after is A and B and X. Maybe X is a bit further up. So that should be 1 and that should be 3. So like 3 to 1 ratio. X should be 3/4 of the way across. So OX, so that's the coordinates we're after. So I want to start at A and then I want to go from A to X. But really importantly, A to X is 3/4 of the way from A to B. So that's the little trick there. OA is just 2, 5. And then I want 3/4 of AB, which was 4, 2. So 3/4 of 4 is 3, and 3/4 of 2 is 1.5. So this becomes 5 and 6.5. So the point X is 5 and 6.5. And if you graph those all out, you'll see it. Next, consider the point D5K. You want to find the value of K, which makes ADC equal 90 degrees. This is another kind of tricky question. So D might sit up here, and you'd like that to be a right angle. So what we want is DA dotted with DB to equal 0. So if we look at this point, so A just pulling these points back is 2, 5, and B is 6, 7. So if you think about how do we get a vector like AB? It's 2 up to 6. Like, how do I get from 2 up to 6? But you can think of this 4 as being like 6 minus 2. And you can think of the 2 here as being 7 minus 5. So if I want a vector like, here's D, which is 5K. If I want DA, it's all the bits of A, so that's 2 and 5, minus all the bits of D. So this is 2 take 5 and 5 take K. So this is minus 3 and 5 take K. All right. And the vector DB, similarly. So it's going to be, let's see, how do I get from 5 to 6? I go up by 1, and I'm going to have DB. So it's the coordinates of B, 7, minus the coordinates of DK. So we would really like DA.DB to equal 0. So this is minus 3 times 1 is the first component. And it's 5 take K with 7 take K to equal 0. That's what we would like. So minus 3 plus 35, take 5k, take 7k plus k squared to equal 0. So that's k squared, take 12k plus 32 to equal 0. Cool. All right, that's good. So, hey, it's a quadratic. I told you that would be useful. I don't really care if you can solve quadratics in Specialist because we covered it in methods. Well, I do care, but I'm not testing you on it. So we can just chuck this into polysolve. 1 minus 12 and 32. There we go, 8, 4. So k equals 8 or 4. You could actually get that with sum and product as well. If you'd spotted the sum and product, you would have got k take 8 and k take 4 equaling 0. But at any rate, k is 8 or k is 4. So we actually have the point d would be 5, 8 or d would be 5, 4. And if you want, you can actually go through and check that you would get 90 degrees there. Who would have thought? Quadratics, they show up everywhere. Z take w here is going to be 2 plus I take 4 take 5i, which is 2 take 4, and it's I take minus 5i. Now, really importantly, you can do that on the calculator as well. Speaking of, I'm going to look at Z take w in simplest form here. So if I go 2 plus shift I and 4 take 5 shift I, I'm expecting 13 take 6i, so hopefully we get that. But ZW is 2 plus I and 4 take 5i. I mean, I guess you get the mark just for writing that because it's a 1 mark question. But I'd recommend showing you working out. FOIL it out, you're going to get 8 take 10i plus 4i take 5i squared, which is 8 take 10i plus 4i plus 5, because I squared is minus 1. So that's 13 take 6i. Oh my goodness, it's the same. Z over W. So if we look at that, you can have 2 plus I, so 2 plus shift I, and the bottom can be 4 take 5i. There we go. Ooh, not list, I. And we're expecting to get 3 over 41 plus 14 over 41i. Seems like a very fun question. All right, so how do we do this? We do 2 plus I over 4 take 5i. The trick is to times by the conjugate. So this is 4 plus 5i. So on the top, you're going to expand it out. So you get 2 and 4, which is 8. You get 2 and 5i, which is 10i. You get I and 4, which is 4i, and you get I and 5i, so that's 5i squared. On the bottom, you're going to get 4 squared, take 5i squared. This will become 8 plus 10i plus 4i, take 5 on the top, because I squared is minus 1. And this will become 16 plus 25 on the bottom. So that'll become 8 take 5. So that's 3 plus 14i on the top. And that is 41 on the bottom. And oh my goodness, it's the same as what the calculator said. 3 over 41 plus 14 over 41i. Find Z plus W and illustrate your answer graphically. So Z plus W is 2 plus I. Plus, and then W is 4 take 5i. So that is Z plus W. So that's 6 to take 4i. And then if we look at this, Z can be 2 plus I. So that complex number there is Z. And W is 4 take 5i. So 1, 2, 3, 4, and down 5. So coming off the end of Z there is W. Coming out from the end of Z, you've got to be really careful about that, not coming out from the origin. And then this is Z plus W there. And I guess we'd better put a scale on here. So 5, 5. And you can see that it is 6 take 4i as well. Minus 5 and minus 5. Pretty much exactly how you'd add vectors. Find Z star, the conjugate of Z is 6 take 5i. Find Z plus Z star. So Z plus Z star is 6 plus 5i plus 6 take 5i, which is 12. Let Z equal A plus BI. A and B are in R. Then z plus z conjugate is 2 times the real bit of z, 2 times a. If you want, you could have like another conjecture like this. Z plus z conjugate is 2 real z. But I'm not going to bother with that extra notation because I've already defined a in my conjecture. Z, so let z equal a plus bi. A and b are real numbers. Z plus z conjugate is a plus bi plus a take bi, which is 2a. Done. There's our conjecture. I'd encourage you to try other conjectures. You could try z take z conjugate. You could try z times z conjugate. Just try lots of things just for conjecture practice. Find a quadratic with real coefficients. So we need to use sum and product here. So the sum of the two roots is 3 plus I plus 3 take I, which is 6. And the product is 3 plus I times 3 take I, which is 3 squared take I squared, which is 10. So therefore, the quadratic is x squared take 6x. So it's always take the sum plus the product. And now it could be any quadratic, so you've got to put a scaling factor out the front, and a is a real number. Now, how do we know we got this right? We can go into equation mode, polysolve, degree 2, 1, minus 6, and 10. Solve, no real roots, of course, because they're 3 plus I and 3 take I. Now, if that ever happens to you, you've got to go into setup, and you want to go down here to complex mode, a plus bi. When you go down here into equation, polysolve, 2, solve, there we go. So a could be any scaling factor. If this was a picture of a quadratic, it would like squish and stretch it up and down. Consider a new quadratic, find the x-intercepts exactly showing you're working. So first of all, 1, 3, 1, let's just cheese it and have a look. So 3 plus or minus root 5 over 2 is what I'm expecting to get. And if I'm showing that working, it's got to be quadratic formula. A is 1, B is 3, C is 1. The quadratic formula is minus b plus or minus square root b squared take 4ac all over 2a. Not sure if that's on your formula sheet. Let's have a look. Yes, it is. Right there, imaginary numbers. Okay, so that's minus 3 plus or minus root 3 squared take 4, lots of 1 and 1 all over 2 times 1. So it's minus 3 plus or minus square root 9 take 4 all over 2. So it's minus 3 plus or minus root of, oh, that's what the calculator said as well, root of 5 all over 2. Excellent. Expand and simplify. 3 plus 2i squared. 3 plus 2i squared equals. Now, there's two ways you can do this. You can write it as 3 plus 2i over 3 plus 2i, and you can FOIL it out. Or if you're confident with your expansion rules, you might remember something like this. A plus b squared is a squared plus 2ab plus b squared. That means that this is a 3 squared plus 2, lots of 3 and 2i, and plus 2i squared. So this becomes 9 plus 4, 12i, plus 4i squared. This is 9 plus 12i take 4, which is 5 plus 12i. Now, if we look at this, we can check it on our calculator. So we can go 3 plus 2i and square it, and we get 5 plus 12i. Find the real numbers a and b which satisfy this equation. So the left-hand side expands out to 3a plus 3i equals 12 plus bi. So the right-hand side doesn't change. So you can read off the real bits and the imaginary bits. So from the real equation, 3a equals 12. So a is 4. And from the imaginary bit, we've got 3i equals bi. So therefore 3 is b. Well, 3 is b. Done. Find this equation. This is a bit nastier. So from the real bits immediately, we can read off that minus a squared is 20b. And from the imaginary bits, we can read off that 2b is minus a. Okay, so a little bit nasty to solve, but realistically, we can do a substitution. So whatever way you swing it, maybe from the bottom equation, so we'll go 1 and 2. So from 2, a essentially is minus 2b. Therefore, from equation 1, minus a squared equals 20b. So minus 2b squared is 20b. So that's minus 4b squared. I'll get rid of the minus sign there, is 20b. So therefore 0 equals 4b squared plus 20b. Hey, it's a quadratic. I told you quadratics would show up everywhere. So 0 is 4b, and we can factor out, so that's b plus 5. So therefore b is 0, or b is minus 5. And then we can just back substitute for a. So I'm going to call this thing star. So from star, a is minus 2b. Therefore a is 0, or a is minus 2 times minus 5, which is 10. All right, so that's what you get. You've got a is 10, b is minus 5, or a is 0 and b is 0, right? Kind of a boring solution, but if you think about it, if all those numbers were 0, you would get 0 equals 0. So technically that does work. Okay, Alice and Bob, they're playing hockey. Alice is there at 2-8 and hitting with that velocity vector there. So every time it's going right 4 and down 3. So 2 up to 6, you can see that's going right 4. And 8 down to 5, you can see that's going down 3. So we've got to continue the pattern. Next point will be 10, so we're going right 4 and down 3, so 2. And then the next point will be 14, right 4, and then down 3, so that's a minus 1. Bob is at 9-7. We can pick any point from the table above. So tell you what, I'll pick the t equals 1. Why not? So Bob is 9-7, and the puck is at 6-5. Therefore, the distance is, well, there's a couple ways you can do this. The methods version would be to use distance is, you'd use this whole long formula. So that is sort of the methods version. But in the spec version, we can work out, let's work out PB, what's the distance from the puck to Bob? Well, the vector. So that's 3 and 2. So that's PB. Therefore, the distance is mod PB, which is 3 squared plus 2 squared, which is a root of 13, which roughly equals, and since this is a real world problem, we probably should do root 13 and see what it is approximately. So 3.61. Groovy. All right. Now this is actually a picture of the situation. So we had this 0.65, and basically what we found there is the distance is 3.61 meters. Now that's actually not the shortest distance. So you can imagine if we took like this point over here, the distance would be a lot longer. I would really, really encourage you to think, what is the shortest distance and how could you find it? And you might want to think about doing like this process, but instead of picking an actual point for P, you can pick the general point, which would look like 2 plus 4t would be the x coordinate, whatever t is, and the y coordinate would be 8, take 3t. So you could use that point for P and then find distance. It's a very fun exercise. Anywho, the point is the puck won't reach Bob, right? Alice fires the puck, completely misses, like, they're not going to hit Bob. Well, actually, it's pretty close, like, not too far away, but the point is Bob can go towards it. So we want to draw a point on the red line such that AXB equals 90 degrees, so it's probably somewhere around there to make that a right-angled triangle. Explain why it might be a good idea. Bob, like the line BX represents the shortest distance from Bob to the red puck line. So that's kind of why he should aim for that. Like, I've never found a really good way to explain why this is the shortest distance. It is true. If you want the shortest distance, it's going to be a right angle. I mean, it just is, because if it wasn't a right angle, you're out here. I'm hoping we can agree that that's kind of like longer than the other line that I drew. Okay, but as long as you just say something about like, it's like the shortest path Bob could travel. That's what I'm after. And obviously 1 mark's for saying that, and then the other mark is for actually drawing the point on the graph. So Bob travels there. You can actually sort of see it. So imagine like this is a vector. Every time Bob travels down 4, have I got that right? Yeah. Every time he travels down 4, he's traveling across 3. So he's traveling like that way. But we don't know how fast. So I've just whacked a K on there. And K, like, if K is bigger, he's traveling faster. If K is smaller, he's traveling slower. Anyway, so that's where that comes from. But what we want to do is verify that this is actually going to give us a right angle if we look at this. So essentially check that VA.VB equals 0. So just as a reminder, VA was from the last bit. So it's all the way up here. Where was it? 4 minus 3. Very start of the question. And this is common in exams. You got to watch out for part A coming back like heaps later on in the question. VB is minus 3K and minus 4K. Therefore, VA dotted with VB is 4 with minus 3K and minus 3 with minus 4K, which is minus 12K plus 12K, which is 0 no matter what K is. So 0 for all K in R. So therefore VA is perpendicular to VB. Therefore this makes the right angle. So this makes APB 90 degrees. So that's the significance. You really do have to explain the significance there. So yes, this vector here, it's traveling in the direction of Bob's velocity. And this vector here is traveling in the direction of the puck's velocity. So we've managed to show that they're at right angles to each other, which is exactly what we wanted. Groovy, all right. Okay. All that. Basically, if you want the position of the puck, you can sort of imagine plugging in like, I don't know, t equals 2 there. What would you get? Well, you get, so 2 plus 4t. So you would get 2 plus 4 is 10. Well, 2 plus 8 is 10. And then 8 takes 6, so you get 10 2. And oh my goodness, t equals 2 gives you 10 2. So that's sort of where that comes from. If you know where something starts and you know its velocity vector, like starts at 2a and there's a velocity vector, it's just the position 2 plus some time times the velocity bit. Same thing for Bob. So that's good. So that's where those come from, just in case you're curious. But we want to find the k and t values so that these two things meet. These two, like P and B, are going to meet at that point X. That's where Bob catches the puck. So we're going to set the X values and the Y values equal to each other. So 2 plus 4t should equal 9 take 3kt. Okay, so that's from the X values. And I'm actually going to rearrange it. So I'm going to put 3kt over onto the right here. I'm going to keep plus 4t on the left. And over to the left. Now on the right, I'm going to get the 2 across to the right. So 9 take 2 is 7. So that's our first equation. From the Y values, so I've got 8 take 3t. So that's that bit there up the top. Should equal 7 take 4kt. Therefore, we can move the 4kt across. 4kt take 3t equals, and then it's 7 take 8. So I think that's minus 1 when you work that out. Just make sure we got all that right. Yeah, looks good. Okay, so therefore we have some simultaneous equations. The top one is going to be 3kt plus 4t is 7. And then the bottom one is going to be 4kt take 3t is minus 1. Now, I don't want you to worry too much about, like, with these simultaneous equations, they look horrible because there's like a kt term. But remember, solving simultaneous equations, you're just looking for two unknowns. One of our unknowns is t, and the other one is kt. Yeah, so it's just like solving normal equations. So there's a couple of ways you can do it. So one way that you can do it is to jump into equation mode, go simultaneous, two unknowns. That's 3, 4, 7, and it's 4 minus 3 minus 1. Solve, bam, and bam. So that's one way to do it. If you want to solve them by hand, I'll show you how you can do that. So what I'd be doing is I'd be eliminating. So I'm going to get a 12 in front of the KTs. So this is equation 1 and equation 2. So I want it to be 12 KT for that first bit. So I've got to times everything by 4. So that's plus 16T equals 28. So this is 4 times equation 1. And then I want a 12 KT here. So that's got to times by 3. So take 9t equals minus 3. And then, so that would be 3 lots of equation 2. So therefore, if we look at 4 lots of 1 take 3 lots of 2, so that's going to give me like 0 lots of kt. 16 take minus 9 is 25t, and 28 take minus 3 is 31. So therefore t is 31 over 25 seconds, because it's the time. So that's roughly going to be, we can work that out. So 31 over 25, 1.24. Now I'm hoping this makes sense, because let's see, t equals 1 was 6,5, so we're off at 6,5. So on the line, that point right there is t equals 1. That's 1 second of the puck moving. And t equals 2 was 10.2. So this is t equals 2. So I'm hoping that it kind of makes sense that this should be t is 1.24. Kind of looks about in the right spot, hey? Anyway, we can work out what the others are. So let's see. Pick any equation. So you could pick equation 1 from all the way back here. So 3kt plus 4t is 7. So 3k, now we know what t is. It's 31 over 25 plus 4 lots of 31 over 25 equals 7. So we can solve this. I'm actually going to show you a really cool strategy with this. So I've got divide by 25s everywhere. I can actually just time the whole thing by 25. So 3k and 31 plus 4 lots of 31 equals whatever 7 times 25 is, 175. And notice that I'm not dealing with fractions anymore. So this is times by 25 to both sides. 3 and 31 give you 93k, plus 4 and 31 give you 124, equals 175. So therefore 93k would equal 175 take 124. We'll just see what that is. 51. Therefore k is 51 over 93. Now you might be concerned about this, because when we did the equation solver, simultaneous to and solve, the t-value looks correct, 31 over 25, but this other value that we found was 17 over 25. So what the heck's going on there? That first number is the first column of our equation. So it's actually that kt is 17 over 25. And then there's like that little bit of extra work to find k, and you'll find out that k is 51 over 93. And if you want, k roughly equals 0.548. Not that it matters too much what k is. All right, now because I know you'll be curious about what this looks like, this is the whole situation here. So that puck line I can turn on and off. But essentially this purple dot is going to move depending what time it is. So depending how far along that dot are, more time equals further puck distance, right? And then we've got a K as a slider here. So K is sort of the speed at which Bob moves to the puck. Well, it's not exactly the speed, but bigger K means faster speed. So where I've got K equals 0 here, Bob's not even trying to move towards the puck. If I set K to something small like 0.3, you can see that he'll try and move towards the puck, but he's going like really slow, right? Never going to reach it. And then if K is a little bit bigger, you can see that he is attempting to make it to the puck, not quite there. K would have to be kind of like something a little bit bigger there. Let's see. Maybe like around that would work. And really importantly, we know what it should be. So K should be about 0.548. So if we set K to like 0.55 and T was 1.24, so it looks like it takes 1.24 seconds, which Desmos is not letting me hit. Anyway, the point is that they're about meeting there, right, when we set our K and T values. And if I set K and T to exactly what we said they were, so 51 over 93, 51 over 93, and then T exactly to 31 over 25, you'll notice that the red and the purple dot are literally just sitting on top of each other. So yes, Bob has managed to catch the puck. Anyway, one more question. We just got to find Bob's speed. So the velocity of Bob is minus 3k and minus 4k, which is minus 3 lots of 51 over 93 and minus 4 lots of 51 over 93, because we know what k is now. Therefore, the speed is the modulus of velocity, so that's minus 3 lots of 51 over 93 all squared, and minus 4 lots of 51 over 93 all squared. I'm going to show you, like, you can just chuck that straight into a calculator, but I'm going to show you a cool thing you can do. 51 over 93 is the thing we just worked out. I can hit the right arrow to store it. Actually, sorry, I'll just hit enter first. Then I'll hit the right arrow to store it. Alpha K. Now, every time that I type the letter K, it's going to come up with that number. So that'll make this a little bit easier to calculate, because all I need to do is minus 3K squared plus, and then minus 4K squared. Saves me typing it out a whole bunch. There we go, 85 over 31, or 2.74. 2.74 meters per second. Done.